We'll just pause
Did you
it.
post
Hey,
the
guys.
challenge in the channel? Oh,
Yeah.
you did. Thanks.
I did.
Dope.
All right, so you can see this a heat challenge. It's a pretty standard heap challenge, a menu. Still not large enough. Yeah, should be large, right?
Yep.
Okay. So this challenge implements a ref count manager. So the typical ref count thing. It's still the typical like node-based challenge. For example, the new, and you will have a node thing, a node array and a size array. We want to create a new node. You can decide which index to put this node into the node array and the size of the node. Pretty lame. But the different thing here is that this node is not like the traditional menu-based heap challenge. This time, it is managed by a ref count. So for a node, a ref count is associated with the node when it does. So let's ignore the RC put, which is a ref count put thing here. We just look at the RC new, which is ref count new. When it does a ref count new, it mallocs a metadata plus the metadata, the size of the metadata, and the size of the node itself, and it sets the something to 1. In fact, it's actually the ref count. Let's call it usage because that's how Linux kernel call it. So it will set the usage to 1 and return usage plus 1, which is actually the pointer to the data thing. If you imagine it as in a sense of the glibc chunk, it actually mallocs the whole chunk first and set the metadata to 1, and then return the data pointer back to user. That's how it works.
I see. And is this so you can't modify the metadata?
Right. So you cannot modify the metadata, but you can control whatever in a data point in a data region.
And the point of the ref count is to make sure that you can't do something like a double free, and you can't have something like more free chunks than you should have currently.
So this ref count has nothing to do with the heap itself. It's a real ref count. Like if the ref count is larger than 0, then whenever you try to delete it, it will not actually free it. It will just reduce the ref count, as we can see in the delete function. We'll try to delete something from an index, from a chosen index. You will take it out, and then do a RC put, and then that's it. RC put is basically take the ref count out and then -1 new ref count. What?
And if it's less than 0, then you free.
Yes, exactly. This is actually the real. It's really how the ref count is implemented in a lot of applications. For example, Linux kernel. Yes, this is how it works.
So why did they have to implement it themselves right here?
This is just demonstrate how to exploit a ref count bug. It's just a toy example, and you cannot actually. I don't think there is a very small library about how to implement ref count.
Okay.
Yeah. All right. So we talked about the new function and the delete function. New function basically create a new object and set its ref count to 1. Delete basically reduce the ref count by 1. If the ref count is equal to or smaller than 0, then it will be freed. Print is okay, we talked about the to functionality. Edit is very straightforward. Take the node out, edit it. So you can specify an index, and then it will take the node out, and then just read line to basically update the content of the node. Shoot. And then there's a print, which is very typical heap challenge thing. You input index, and it will print whatever in the nodes at that index. Yep. So far, everything is very good. The ref count is implemented correctly, except in this very interesting copy function. This copy function is super small, but actually it's vulnerable in a very not obvious way. Let's see. So in this function, it takes two arguments. One is actually two inputs. One is from index and a to index. Basically, it implements a copy functionality that you can specify that you want to copy the content of a from index node to another node. You copy whatever of it into that into the to index. So how it is implemented? It directly take the node out from node and do some sanity check here. If such a node does not exist, just do nothing. So you make sure from node and to node do exist, and then it RC put. Remember, ref count put is decrease the ref count. So it will decrease the ref count of the to node, and then increase the ref count of the from node, and then copy the pointers and size from the from node to the to node. Look at this: node to index to equal to from node, which basically assign the pointers to the to indexes node. Looks correct, right? You when you copy a node, you increase the ref count of the from node, and then decrease the ref count of the to node. Sounds legit, right?
Yeah, I'm trying to see the bug. I don't see one yet.
Yeah. So in the first side, me neither. And then I realized that, wait, what if from and to are the same thing? When you created a new node, the ref count is set to 1, and it reduced the ref count first. If the from and to nodes are the same thing, when you do a RC put, the ref count will reduce it to 0 and gets freed. And even yeah, so even if you later increase the ref count, it doesn't matter. The object has been freed already. This is the interesting part. So basically, we have a use after free. But so let's check what primitive do we have.
So wait. Where does the use come after the free? Because I see you can get the to note, you can get it freed right there with the RC put. But then where is the to note used again?
But you have reference to it. You can still edit it or put or show it, right?
I see.
And the thing is that the from note is the same thing as the to note. And
no, I get that. I get that. I'm just asking where do you use it again? But I understand now. You have the index reference, and you just choose that for edit. Or
God, yeah.
Yeah. And the good thing here is that you actually, by doing so, you actually have two references to the same freed object, right?
Yep.
When you do because when we trigger the vulnerability, the from and the to nodes are like this will be set to the same thing. The pointers will be the same. This is actually very useful primitive when we're exploiting the bug. All right, so we're done with the IDA. So let me share my screen of my exploitation because there is something wrong with i3 and Discord. I have to close IDA and share my terminal. Oops.
Oh, you can change your screen without closing the sharing. Yeah, with the little share button in the bottom left of your screen.
Oh, actually, it doesn't work on Discord because Discord does not capture the i3 screen change.
No, I mean you can select a new screen without closing the.
No, it does not capture the change. It will still show the IDA screen. Oops. Oh, what I'm doing. Oops.
So like, yeah.
Yep. So you see my
Yep.
Not only, right?
Could you increase the font like just a little bit?
Sure, of course.
Thank you.
Okay. So this. All right. So first thing first, disable everything. So we know that it is a use after free. Then, and we actually have references. We actually have references to the freed object after the vulnerability is triggered. So getting the heap leak is supernatural. So that's the first thing we're gonna do. So what we need to do is just basically allocate two objects. Why we need two objects? Because actually one is enough, but let's say we have to. This is.
Do you do that just in case it gets consumed? One of the chunks.
In fact, it's not because it's. I do this because later I'm going to use it. Actually, do one allocation and show will be enough. But let's see it. Let's do it again, like from scratch. Maybe let's just copy soft to bk soft back soft pi and then let's modify this exploitation. So we do an allocation. We allocate a node at index 0, and we trigger the vulnerability, which is at this moment the node will be freed. Actually, let's say the chunk will be freed, and then the chunk will be something like 0 and a key pointer. Let's verify that in. This, that. Yep. Let's see that in B. Okay. What? No, don't do this to me. Yep. Damn. All right, as you can see, this is the object. The ref count has been increased to 1 again because because of how the vulnerability is triggered, it will get freed, and the ref count will be increased by 1 again, right? So this part is the ref count. It's increased by 1 again. And here is the key pointer. I think we talked about the key pointer last time. It is a pointer pointing back to the Tcache per thread struct, just for double free detection. In short, it's basically a heap pointer. And remember that this part, starting from this part, it's our data region, because the first pointer is the ref count region. After the first part, here is our data region, right? Yep. So theoretically, we can leak the heap base directly by print the 0 node, which is 4, 0. As we expected, we get a heap leak very easily, right? This is 555 something. So apparently this is a heap leak. All right, we got a heap leak, but what next? Because of how the ref count works, in fact the free list will be corrupted. You'll end with a 1, which is bad. If we locate one more chunk, it will be fine, but one more, like 2 more chunks, it will crash. Theoretically, it will crash, but in fact, it will not because of the chunk check here. It will not crash, but it's still not good for us. Wait, I think I didn't. All right, so we gotta use up the free read. We get heap leak, but how to get a shell? We need something to hijack the Tcache free list. So we need a use up the free write. This comes natural because of the nature of this vulnerability. Think about this. If we allocate 2 chunks and we trigger the vulnerability twice, what will happen? This will make the this will add 2 entries into the free list, which means there will be another pointer pointing to this pointer plus 1. Let's see what will happen.
Oh, I see, and it overlaps a little bit.
Yep. Well, actually, it's 2, right? 1. Okay, cool. You see, it's similar to the last time what I showed last time. Because of how the glibc works, when it frees the second time, it will add a pointer here, which is the last freed Tcache, right? So it's a Tcache pointer, but because of how the ref count works, it will add 1 to whatever it was here, so it becomes a pointer plus 1.
Oh shit, I see.
But
that's a cheeky little ad. I didn't realize that.
Yeah, it's an add 1. And the good thing here is that, so usually when we are at this position, we will think, oops, the free list is corrupted. But think about it, this is Tcache. Tcache does not have any security checks besides the double free check. So it does not check whether this chunk is aligned or misaligned. So to Tcache, this is still a valid chunk. So what we can do is here is that we misalign this chunk because of the ref count. This chunk is misaligned, but still it's valid. It's a valid chunk. We can take it out and override the size of the next chunk. Think about this. If the chunk is misaligned by 1, right? Which is should be 40, let's say. It points to 2A1, which is here. And we can override 20 bytes after that, which is 20 bytes, which is 20? No, 10. We can override 10 bytes, which is here, which will override 1 byte here. This byte is very essential. It's the size of the next chunk. So if we can override that, and we can, for example, we add some more chunks here, and we make it like 81, and we free it, this will cause a chunk overlapping. If you have it, did you see the plan here?
Okay, I see. So you're going to change the size of the next chunk, which will be bigger than what it actually is, which will allow us to overlap another chunk and arbitrarily overwrite the pointers there.
Exactly.
What about the key?
Oh, the key doesn't matter. The key only works when the chunk is freed. But oh wait, there are two parts. So the first part is we already get a heap leak first in the first place.
Right. We had that.
And
earlier.
the key thing is just a heap pointer. We can forge it, right?
Okay.
This is the first part. The second part is we don't care about the so in a chunk overlapping, we actually don't care about whatever is in the inner chunk. We can partially override whatever is in it because we control the outer chunk. Think about it. Suppose this is a outer chunk and this is an inner chunk. We don't have to override the key part, right? We can partially override this part to control the Tcache free list.
Yeah.
That's
okay.
That's the answer to your question.
That's a pretty good plan. So you have these two chunks. So the key component that allowed you to do this was being able to modify that single byte because of the single overlap, that 1 byte overlap that they did because of the ref count, which allowed you to access the size and the in-use byte of the next chunk.
Exactly.
So you just change the size and make sure it's in use, and now you have overlap, which is pretty much, from what I've heard, is end game. Once you can overlap chunks in Tcache.
Yes. So chunk overlapping is basically the most powerful primitive that you can have. But usually you don't get this primitive directly. You need to escalate from other primitives. But
right.
Actually, that's not the end game here. Both Jai and Klasm got this part, got here, but they didn't manage to solve it. So the problem here is we have heap leak, but what we need is actually glibc leak. Heap leak by itself doesn't help at all. Well, we need glibc, right?
Yes.
So to get the glibc pointers on heap, the best way we know is to somehow free a unsorted bin, right? So that actually means we need to override 2 bytes of the size, not just 1. We need to override 2 bytes, make it like 4 to 1. That would be ideal. So that's the plan, and that's what I'm going to show here. So here, instead of doing 2A1, we increase it to 2A2, and that's it.
Yeah, that's what I was thinking. You just get the ref count up one more time, and you can.
Exactly.
Is that why you have 2, or do you just do it twice on the same place?
Like no, you don't. You just increase the ref count, and you can copy it, or copy it. It will increase the ref count, right?
Right. Yeah. So you copy it one more
just
time.
Copy it again.
Brilliant. So Klasm missed this?
No, it's not that easy actually.
Damn.
So we're here. So so the code here is basically what I showed. We do allocation, two allocation and trigger the vulnerability twice, get a heap leak, and then we copy the one. One is the free
the one
object.
we copied earlier.
Yeah.
Yeah.
So we copy it again to increase the ref count so that we misalign the like one more byte. Then let's debug it. Cool. It's 2A2. Exactly what we thought, what we had in mind.
Roger.
All right. So next plan is to override that thing, but case is to take it out. Yeah, we do two allocations, and then we can take this chunk out and take this chunk out, and this chunk will overlap with the first chunk. Let me show it here. If we do two allocations, the first one will be here. The second one will be 2A2, which is misaligned, which is here, I think. Here, I think. Yep. So eventually we can override the size, but not right now. We can override the size, but it's still not that good at this moment. So do it. Well, okay, two chunks, good. The problem here is that there is a check in libc that you cannot directly like increase the size and then free it. But let's do it. Let's so here we will get two chunks. Let's override the misaligned chunk, and then we override it, which is edit for e plus. Let's do 2104. Let's say. Yeah, exactly what we expected, right? If we free it, I mean, we're expected to get a unsorted being like libc leak here, but it will not. We will not get it. It will crash. Let's say delete 4. This one is 4. It'll crash. This says invalid pointer. So what's wrong here? So this is a 2.31 glibc source code. Let's check what's going on. What's wrong here? Wait. Tab stop is equal to 8. Cool. So wait, what? No, this shouldn't happen. Oh, this is a real lock. That's why. So it checks the misalignment and size. Chunk size.
So if it's misaligned, it gives an invalid.
But it's not misaligned.
Wait, but I thought it is misaligned by 2. And
No,
the
it's not.
By 8. No.
Hey Siri, pause. Are you?
What the? Wait. Oh, I'm sorry. So we override the. We should try to free this one instead of this one, right? You're right, Lucas. So the 4 one is misaligned. Yeah, that's why. We should try to free 3, right? The free is the chunk that with overwritten size. Yeah.
Yes.
Let's try to free 3. But you will crash anyway. What the? Choice is 4. No, 4 is show. We should do 5. 3. Okay, it crashes. double
Alright.
free or corruption. So what is it? Fast top. No. This one. This one. Proof in use. So it does some check on the proof in use next chunk. Next chunk is very obvious, which is the next chunk. But in our case, because we override the size, there's no such thing as the next chunk. You see you see the point here? So we override the size to 421. And then so the next size will be the current chunk plus 421, which will point to 0. So when it checks the proof in use, it will return 0. In libc, you will think that, which means the chunk that we are trying to free is already freed. That's why it crashes. Let me demonstrate that. Not demonstrate. Let me illustrate that in memory. So this is the chunk that we want to free. And the next chunk it points to here, which is 0. And libc is trying to check whether the last bit is 1. If it's 0, that means in glibc, that means this chunk is already freed. That's why it crashes. So what we want to do is just set this bit to 1, and that's it. Actually, not 1, but like a valid chunk. We create a valid chunk here, and that's it. We can bypass the check of libc.
How far away is this from our chunk that we controlled? Or it's actually, is this in the overlapped region?
This actually is not the overlap region. Top chunk is here. This is the never used region. So what we want to do is just allocate a loft chunk, and we allocate a chunk here, and that's it.
How do we assure that the alignment is correct for that to end up right there?
So right now, the misaligned chunk is already taken out. So the misaligned chunk is taken out, and the glibc is already in its like a right state. Everything is right, is correct. Although probably the Tcache is corrupted, but it's fine because the count is 0, so you will never affect anything. Tcache is not going to take this chunk out, so the allocator is in a good state, so everything will be correctly aligned.
Okay.
Yep. So the plan is we make this chunk valid. We override its size, but we want to make it valid, and that's a little bit hard. That's where Will got stuck.
Kyle, if there was already a 1 there, would we be fine, or are there other requirements on the bytes there?
There are other requirements, and it's not just 1. But
Yeah.
this is kind of easily satisfied, or can be easily satisfied if
we just need to create some chunks to get there, right?
Yeah. So that's one way. The other way is we allocate a lot of things here, and we override its content to make it a valid chunk. It looks like a valid chunk.
But then you need to know the other constraints, right?
No. So when you do, it's free is stateless. When you do a free, it only checks like the adjacent chunks. It does not check like everything. It checks the adjacent chunks. We just put a fake chunk here. It doesn't matter because it does not know. glibc does not know this is a fake chunk until we will try to this fake chunk. Then glibc will check whether this is a fake chunk or not.
Right, but to do that, it's going to look at those 8 bytes, right? And one of the constraints is that the last bit has to be a 1. What are the other constraints on that, on those 8 bytes?
8 bytes, you mean the size or?
Yeah, exactly the size.
So the constraints is, there are a lot of constraints, but the most common ones is that the last byte should be 1, which means the previous size is in use, and the size is a valid size, which means at the chunk plus this size points to a valid chunk. That's basically the checks.
Okay.
Yeah. So if we want to create a fake chunk here, we can do a 21 here and a 21 here. The first 21 makes it a valid size, and the previous size is 1, right? And the 20 here, because I will want to set it to 21. The 20 here makes the next, make it a valid size. So that this is complicated.
No, I think that makes sense, but you don't have to make then the next 20 bytes later
Right.
also be a 21. It stops
Exactly.
there.
Exactly.
Because it doesn't walk the entire linked list. It just looks at surrounding ones.
Exactly. glibc only makes sure that next chunk is a valid size. How valid it is? The previous in use size is checked, and the size is a valid size, and that's it. To make it a valid size, you just make the next chunk is a valid chunk. That's it. All right. So we have the plan. We just make the here, which is put a fake chunk here. So and then we can free our fake chunk. All right. Not fake chunk, but the chunk with an overwritten size. All right, so this is the bad code. But we also need to create a victim chunk, right? We wait, what? Okay. This is it. Why we need to create a victim chunk? Oh, to create overlapping. So we tried. We said that we can get a. So we talked about that. We can override size, and then we can free it, and then we can get libc leak. But to successfully perform the exploitation, we need another thing, which is the ability to override the free list, right? Let's forget about it. Let's forget about this allocate victim chunk part. Let's start here. Let's start with the glibc leak glibc logic first. This part is quite easy. We just do a lot of allocations. Let me do one at a time, maybe. So we do. So the idea is we exploit how Tcache works. So Tcache works that it allocates the exact chunk. So if you request a like 20 size chunk and you have a free chunk with 70 size, then that chunk will never be taken out, right? Let's say that chunk is a memory leak on heap. What we can do is we do a lot of that thing. This make it a chunk leak of, this is a, god damn it, I cannot explain it. Let's do it. So we allocate a chunk of this a large size and we delete it. You can see that that thing is added to our to the heap. It's here, but we're not going to take it out because our target Tcache is of size 20. And then we do this again and again and again. We're going to push to our targeted location. Do you see what I'm doing here? Okay, it's confusing. So our goal here is to make this place plus 420, which is here. What we need to do is to make this, to put a fake chunk here, but our heap usage is stuck here. So what we can do is to we free a large Tcache chunk here, but we never use it, and then it will becomes a fragmentation here and be left on heap and never get used. And we do this for a lot of size, and eventually we are going to use this part. If we can use this part, we can put our content here. We can make it a fake chunk. Is that clear? Kind of.
I mean, so all of those sizes add up to approximately hex 420 once you account for the metadata?
Yep. That's what we want to do.
Yep. I mean, it's just weird that you're using different sizes. Why do you need to use different sizes?
Because if we use the same size, this, for example, we use F0, and then this chunk will be used. We don't want.
Oh, because we're freeing it, right.
Yeah. So what we want to do is to use it, but use it once, but then never use it later, so it will be left out.
And we can't just malloc it but never free it?
What do you mean?
Like, why can't we malloc a bunch of F0s?
Oh, we can, because there is, yeah, we can. Theoretically, we can, but because of how the challenge is implemented, it only allows 5 nodes.
Oh, okay.
Yeah, you're correct. So we can do a lot of allocations, and that will help too. But because of how this challenge is designed, we can't do that. We have to make it like freed on here.
Yeah, that makes sense.
Yeah. So as you can see, now we have control here. This is the top chunk. The top chunk has been pushed below the region that we want to control. Right? This is good. So we have control over here. So inject whatever we want here. That's what I did. What is it? Oh, here, this. Now we can put a good chunk, a good size here. What is our target chunk? Should be this one, right? 2d0 plus. What? It's not edited. First, low. Looks like there's. Oh, yeah. It's somewhere here. Oh, okay, there is a misalignment here, so we have to make it like 4 and 6 maybe. Yep. Yep. Now we're here. So we already. This is, damn it. This is a chunk that we control size, and we want its next chunk to be a valid chunk. This is a valid chunk because it has a good priv in use bit set, and its next chunk is the top chunk, which is another valid chunk. Now our fake chunk, which is this one, is a valid fake chunk. Now we can free the our chunk with overwritten size, but we need to override its size now. How to override its size? It's 4, right? This one. Now look at this. It's very similar to what we had before. Instead, but there's the only difference is that we put a valid fake chunk here. So now if we free this chunk, then you will glibc will be happy about it, which is 5, right? 5. Oh shit, this is not 55. 5. 3, I think. Yep. You see, we have a unsorted bin here. And it's at this location. Anybody gets what I'm doing here? What we're trying to do is to get a libc lead here. And how I did it, I override the size of chunk and then bypass the checks in glibc. How I bypass the checks in glibc, I'm abusing the Tcache fragmentation mechanism to put our valid chunk valid fake chunk size there. Oops. Oh shit. No. Oh no.
So Kyle, originally this was a Tcache chunk and we turned it into an unsorted bin chunk, right?
That's what we did. But
how does libc keep track of where its unsorted bins are at, or unsorted chunks are at? Because initially, right, it was sitting in a Tcache linked list. How did the unsorted resolve and find that? Does that question make sense or no?
Can you say it again? Because my
you-
Discord crashed.
Oh, okay. Yeah. So how does libc resolve unsorted chunks, right? Is there a linked list structure similar to Tcache?
Oh, so
because it was initially sitting in a Tcache linked list, right? And suddenly it becomes a unsorted bin. I guess I don't understand exactly how that happens.
Oh, so this it's not like it's in. So originally it was not in Tcache. It was a chunk with size 20, and
because it was allocated
21.
and then we free it and then it becomes.
Yeah.
I see. Okay, yeah, makes sense.
So we didn't move it from Tcache to unsorted bin.
Right. It was an allocated chunk. Okay.
Right. It was an allocated chunk. Can you see my screen now?
Yeah.
Okay. My Discord crashed. Oh my god, this is bad. Yes. Now this chunk is freed, but because of how we exploited the vulnerabilities in the first place, we still have reference to this chunk, so we can leak the libc addresses here.
Was that the first one we had?
The first one? The first one is a heap leak. This here is the libc leak.
Oh, this is 3. Okay.
Yeah, this is 3. But 3 is deleted. We need another reference to it. I think it's 1. Show 4.
Also, Kyle, another quick question. With that unsorted bin that gets allocated, what are those libc pointers semantically? Like, why do those suddenly get added there? What are they pointing at?
It's a doubly linked list.
Why is it pointing at libc though?
So you have to have something to that's how doubly linked
the head
list.
lives in
Yeah.
libc. I
Yeah.
see. Okay.
Yeah. So if you check, let me directly just check whatever is in there. No. This one.
And how do you find the head offset in libc? Is it a symbol?
The head offset?
Yeah, like you get this libc address, but then you need the offset of where it's located in libc.
Oh,
Is it a symbol?
it's somewhere after malloc hook.
So it's somewhat random.
No, it's build dependent, but it's so the offset cannot be determined like static. It can be.
There's not a symbol for it.
And there's
Yeah,
no
that's what I
symbol
was
for it.
asking, the
Yes.
symbol.
So what I do usually is I leak it and this is how I do it. I leak it and I minus the malloc hook and then print it. So there will be something like something and an O and offset.
I see.
And
And
I
you just
minus-
check for
minus
when the
that
end
one.
is 0, 0. Yeah.
Yeah. And make sure.
This is something that Connor hates.
That's true.
He
It's
despises
field
this.
dependent. This is what
Yeah,
can
but
we
why
do?
would you subtract 7-0 when you could just bit mask it out, right?
What?
Then it'll always work.
What do you mean?
Because it's gonna have libc's gonna have to be page aligned, right? So why not just and with FFFF 0 0 or whatever?
Sometimes I do that too. Actually,
Hey, it's
I just
cleaner.
want to make sure
Cleaner. 70 is a magic constant. I don't like magic constants.
Yeah, he hates that shit.
I sometimes do that too. Yeah, I use both methods.
Yeah.
All right. So, we get here. So we get a libc leak, and this is actually already the end of the game. We get the libc leak, and we have use after free, right? We can allocate it anywhere, right? That's it. That's done. But instead of doing a very sophisticated attack like what I did here, maybe we can do something easier this time. Let's delete whatever I have before. Wait, what? Okay. Oh no, I need to copy the leak thing.
So I got a question for you, Kyle. When
Yes.
you have overlapping chunks, is the point usually to change the size of the chunks and get a leak through fastspin, or it can it be completely context dependent? You know,
Nobody
like
uses fastspin nowadays.
Oh damn, fastspin is dead.
Yeah, fastspin is dead. Almost,
Oh,
but it's
shit.
not like it's just whatever fastspin can do, Tcash can do it. Then why do we use fastspin?
Okay. So what do you usually use an overlap for, aside from this specific example?
I use Tcash. And
You
sometimes
use it to override a forward pointer, right? So you
Yeah.
can arbitrary right.
Yeah. Okay.
wait, what? What's going on? What's going on here?
So how do you usually leak libc in those cases?
Sorry. Can because it doesn't make sense to me. Can you say the question again?
How do you usually leak libc in those cases when you're just inside of fastspin? Or sorry, not fastspin, Tcash. Because you said you would use an overlapping chunk to overwrite the forward pointer, which makes sense, but how do you know where to go?
Oh, so let's say, wait, exactly like this case. When we have chunk overlapping, then we override the size of the overlapped chunk. Then we free it.
Yeah, and you did that so you could get the libc leak. So is that usually what you do?
Yeah, that's usually what I do.
Okay.
Because
aren't there other libc pointers on the heap though?
I don't think so. Like there are several cases. Large bin can have libc pointers. Unsorted bin can have libc pointers. Small bin can have libc pointers, and that's the only cases. They're basically the same, right? They're doubly linked lists.
For some reason, for writing the Pwn College challenges, the way I've always solved it is just grabbing some random libc pointer out of the heap that just randomly happens to be there, and it's always been there for me.
Oh god, this is bad.
It's always been there without issue.
This is a terrible approach.
What do you mean? It's always worked. I want to know why you think it doesn't always work.
It does not. Because for example, if you set an up limit of the chunk, the size of the chunks that you can allocate, then you will never get a glibc like libc pointers on heap.
I don't know. I might have to look into this more. Feels like they're just there from the start.
No,
like without any allocations.
Actually,
I think
you're
there's a libc
right.
pointer.
Because Pwn College challenges can be a little bit complicated. When you open a file, when you do for example, fopen, then there will be a libc data structure allocated on heap, and
that has the.
Oh man,
okay.
Yeah,
Maybe I guess that must be it then.
it's the format of Pwn College.
Yeah,
Nice.
this is bad. then it makes like heap exploitation much easier.
Yeah, that's the goal.
Oh, very good. It's intentional.
Intentional.
Yeah.
All right, so let's finish it, maybe. Oh God, where is it? What happened? Oh, delete 3. God damn it. So delete 3, and we show it. We should get a libc leak here, right? Yeah, we do. Cool. So we have heap leak and libc leak, and we have a use after free. This is basically end game. All right. So how do we do it? We use all the use after free thing to overwrite the forward pointer of a chunk, and that's it. But wait a minute. There is something wrong here. Remember that we don't control. Remember that the first 8 bytes is actually the ref count, right? So we actually cannot override the forward pointer. This is bad, right?
But I thought we had an overlapped chunk.
Yeah, that's the solution.
Oh,
but
okay.
it's complicated because of how the challenge is designed. It only allows like 5 allocations at the same time, right?
Mm-hmm.
It makes things a little bit complicated, and that's why you actually see a allocated victim before I do the size overlapping. Before I do this, there was a code like allocate victim. So what I did is what I did here is I allocate a victim here so that I can perform the chunk overlapping later. Oh, sorry. So we can actually have a chunk overlapped chunk here, and then overwrite the pointer. You see that? No? Okay. Alloc. Maybe 0, not 0. Maybe 4, 2. Don't remember. Let me check. Create 0. Okay, allocate at 0.
So a potential issue. So we currently have an overlap chunk with that unsorted bin that had our libc pointers, right?
We actually don't have overlap chunk. Technically, we don't. Because we don't have a chunk that is in our control within the large chunk.
Oh, we only are overlapping over the size.
No, we add a lot of paddings here. We have a lot of paddings here.
I see, right. Yep.
But we don't have a chunk that is in our control within this part, right?
Okay.
Yeah, so
Because
we need to add it.
Never kept a reference to it, basically, or what? Because we just kept, you're talking about all those chunks that we freed of different sizes, right?
Yeah.
And we don't have a reference to any of them?
Exactly.
Basically?
That's the
Okay.
problem.
Yeah.
So
we just need to keep a reference to one of them.
Yeah. Yeah. So there are multiple ways to do it. So previously, what my approach was to allocate a chunk here, so we can reference it, and then we free this chunk, victim chunk here, and we override it from the outer chunk. Right? That's my previous approach. But there is another potentially easier way here that I want to try. Let me try it. So instead of allocate a victim here, instead we allocate to this kind of thing. Oh no. Oh, my math is off. This should be A, B, C, D, F, and then A, I guess. F, F, D, C, A, so that the size will be the same every time. And then this time should be 3, I guess. But actually this won't work because we don't have enough reference here. We have 0, 1, 0 is in our use, 1, 2, copy 2, 2 is 2, 3, 4. We can't free 3 at this moment. Yeah, we can free 3 here. And then we do this, and do this. Okay. So what I'm trying to do here now is instead of trying to insert a victim chunk within the overlap chunk here, I'm going to allocate 2 chunks that of the same size and then override its pointer. This sounds complicated. So like we have a lot of fragmentation here, right? And none of them has a pointer in a forward pointer here. Everything is null here. What we want to do is to make one of them have something here instead of null. And we hijack that pointer to wherever we want, like a free hook. I'm not sure whether it will work, but I think it will. Let's do it. This. Yep, it looks good to me. So what we want to do is we free this chunk first, and then we free this chunk, and then this forward pointer will point to here, right? Oh, sorry, will point to here, and then we override this pointer from this chunk, from this outer chunk. Then we're basically doing a T-cache poisoning. This is not very intuitive, but let me finish the exploitation and then explain it. I think it's down here. Down here. Oops. Now, yes, we have a good. Yep, we have a good thing here, and then wait a second. Wait a second. And then we delete 3. Oh. No, it's fine. Yep, now you can see that we have a pointer here. No, we don't want it to be here. We can move it. We can move it up here, so it'll be easier for us to overwrite. So I can locate F0, delete 3, delete 0. Cool. Oh, damn it. Okay. Yep. You see what I'm doing here now? This is our outer chunk. This is our inner chunk. But within the inner chunk, we have a Tcache linked list exactly in our inner chunk. We can override this pointer.
Which index is that one?
Index? There is no index here. It's
so
free.
we don't have a reference to it.
We don't have a reference to it, but we're attacking the glibc allocator. We're attacking the allocator directly.
But when we malloc size F0 or whatever, we'll get that forward pointer.
Right. Yeah.
So basically, override this thing directly, which is here, right? All right. So we free it. We free. Wait a second. Instead of doing the size of reading here, to C0, it's already freed. Now we don't free it here. We do it here. We allocate it. We'll allocate 3 again with 10. And we edit it. Its size. And then we free it. Now we can get the libc leak again. Yep, we get the libc leak again. And then we check what's going on in our heap. This angel heap is pretty amazing. It directly it captures what's going on here. Our chunk, everything is overlapped with this unsorted bin, which is this one. This is our outer bin. Oh shit. And this is our inner bin. Our inner bin is here. But it's corrupted. Doesn't have the size here. Our inner bin is here. The bin, the chunk that we want to control is here. You see why? Does anybody understand what I'm doing here?
I mean, right now we're just trying to overwrite the forward pointer. Are you saying that there's some sort of hurdle?
There is no hurdle. I just want to make sure that I'm understood. Okay. So yeah, we have an outer chunk, and this is the inner chunk that we want to do here. And we want to override here, but the size is not. The size is cleared. It used to be 101. It used to be this one, 101, but it's overwritten and written as null here because this chunk is large, and these 2 pointers, these 2 nulls are actually 2 pointers, which corresponding to the forward next size and backward next size thing in large chunk. Not related to our exploitation, but I just want to explain why the size disappeared, because it used to be 101.
So we
need
gotta
to put the size back.
Yeah, we gotta put it back.
We need
in use.
Yeah. Oops. Oh no, okay, cool. So what we can, because every Tcache free list is kind of corrupted, especially the 20. We just allocate another size.
Jeez, man, this Tcache is so fucked up right now. I didn't know you could make it this fucked up and
No.
get away with it.
No, it's not fucked up. It's not fucked up. And the only problem here is that we're doing a chunk overlapping, and then this plugin will detect the overlapping and mark them as corrupted. But they're actually not corrupted to the libc view.
Except that F01's missing its size, right?
F01? Oh yes.
The first one we
That-
talked
Yeah,
about, yeah.
But everything
one.
else is fine.
Yes. So what we can do is we allocate like 40 or 30 that's not in Tcache, and then because there is an unsorted bin, libc will cut that chunk out of the unsorted bin, which is here. So we can replace, like, put our size correctly back to here, and at the same time override the forward pointer. All right, let's do it. Allocate what? Allocate endgame. Allocate. Let's do 30, and then if it's 30, then it will be this will be ref count. Shit. This will be ref count, and this. So 10 paddings, one size, one pointer. Okay. Locate and edit 0, which is 10 paddings plus a size. What size do we want? Which is 101. And a forward pointer. Let's do free hook.
So, okay, wait. So that first overwrite, you're overwriting both the ref count and the next thing next to it. And then you have the size as the last thing there, and then you're doing the free hook, which will be the forward pointer. Right?
Yeah. So this will be the ref count, right?
Yeah, ref count gets overridden with zeros.
Yes. Actually one.
Oh, but you put 0.
No. Because
miss
ref
that?
count is not in our control. We don't control ref count.
Okay.
Yeah, we don't control ref count. So this part it will be 1, and then we put 10 paddings here. This will be padding. This will be our size.
Yeah.
This
And then the forward pointer.
Yep.
Got it.
But instead of doing a free hook directly, we need to -8 reserved for the ref count. And we'll do some calculation. Free hook. Okay. We are good to go, I think. Let's see. It's so fucked up. The heap is so fucked up. This fight doesn't matter.
So which heap plugin is this?
Angel heap, the Pawn GDB, not Pawn DBG, Pawn GDB. So we're actually hijacking the free list to 8 bytes before free hook. Cool. Then we do a allocation. We do a allocation. Let's do it at 0 again, F0, and edit it with system. Let's not do system. Let's do system. Right. System. I'm lazy.
Don't you need to allocate twice?
What?
Don't you need to allocate twice?
Why do we need to allocate? Oh, yeah, you're right. Do we? Yeah, we do. So, which is 4 is corrupted. Let's do 3. And then I'm lazy, so let's do 3 and the system at the same place. So instead of doing system directly, we do Bing sh, and then this one. This is our payload. Because it's -10, the system will be placed at the free hook correctly, and we still have something more as our payload. Let's see whether it works. I think it will work.
Wait, that
no, it
works?
crashes.
That sounds insane.
It works because of the show earlier. It's gonna put it in RDI, and then he's gonna call system like a fucking legend.
Wait, what? I'm so
Yeah,
confused right now.
it's gonna be great. Watch. He's done this trick to me like 8,000 times, man. And every time I'm like,
I don't know.
whoa,
You
that's
just
so
put
crazy.
Ben SH before your system address, and it just works. That doesn't
He
make
does
any
this,
sense.
dude. He does this in every single pwn challenge I've ever seen him do.
How
It's
can that
insane.
even possibly work?
He gets it into RDI. It's madness. It's awesome. It's like so pwn like. It's amazing.
Yeah, you see, system is already at the location of free hook, right?
Yeah, that makes sense. But you need
Yeah,
to
that makes
get
sense.
spin SH into RDI.
Watch what he does.
Show, it's show, right? We can't show what's going on here. We show it, so
Now it's in
SH is
RDI.
there.
Oh,
then we
because
do-
it's printing. I see.
Yeah.
Oh,
Now he
no.
put it in
Oh, no.
RDI,
Yeah.
and then he calls system.
Crash.
He does this
Why are we
every
crashing?
time. He does it every time, dude.
Wait, you can't always do that, right? That's just because there's this show functionality that will do like a puts on whatever thing, and that'll put it into RDI, right?
There's always a way he does this, man. It doesn't
I mean, there's
matter.
probably a lot of like move into RDI gadgets that you can just like.
He doesn't use
Not true.
gadgets. He
Well, I mean,
always...
it's not like technically a gadget, but you can basically get RDI where you want it to be.
I mean, a function call could be a gadget if you really want
Yeah,
it to.
exactly.
Yes. Yes, he always puts bin sh and system in the same payload and then uses the first part with a null appended 0 so that he
Smart.
can print it and then it's in RDI every time. Every single time.
No, but it's not work this time. This is
Love it.
weird. This is weird. Let's see what's going on here. So we managed to but yeah,
You should
it
have break on
work.
system, right?
It should work, right?
Are we not even hitting system?
Yeah, we're hitting system, but somehow it's not triggering the Bing SH, which is weird. Probably I did something wrong. Let's see.
Probably because it's insane.
It's insane. No, it's not insane.
Dude, it is
4,
insane.
0. Oh no. We're to 4, 0. What? 4 is what? What is 4? Let's see. 4 is show, right? Oh god damn it. Yeah, it's being SH. That looks correct. Is it? Let's set a breakpoint at system, and then we do. Oh no, it's not. It's not. Oh shoot! I think I'm being dumb. Wait, no. This is weird. So this should be our payload. But it's not. But it is. What? Huh. Oh no. Oh shit. So this is kind of a different. So there is a different thing here. Damn it. When we do a free, we're actually not freeing the. We're not freeing the our payload directly. We're actually freeing the ref count. I mean, the RDI is actually our ref count, right?
Oh, right. Yeah.
Yeah. But
Yeah, RDI got
actually,
fucked up.
I did the same thing in previously. What I did is I put a my payload here as a ref count. You see? So what you can do is you put your payload here as a ref count, and that's it. Let me think how to do it in this setting. So we cannot directly do it. Why not? Because why not? thing.
Yeah,
Dude,
exactly.
it is crazy.
It's not. It's not.
Wait, so our
pretty
ref
fine.
count is ending up in RDI, is what you're saying?
Yeah. So this time RDI, this part has been taken by RDI. Oh, sorry, by ref count. So we're basically freeing the ref count. Looks like. Let's see one gadget. Oh, one gadget won't work on this newer version. Oh crap! I'm doomed.
I'm doomed. It's over.
It's over.
Time of death. Call it.
So we have to do the traditional chunk overlapping thing.
No.
No, I don't like it.
No. Do the thing you always do. Do
the thing I always do. Okay,
do the
fine.
thing, man.
It's not hard. It's not really. It's really not hard. Let me do it. Instead of doing it this time, we can delete 3. And then we are having a chunk overlapping. So we allocate it again. We allocate what the... We allocate... we cannot free that thing. So we free 1 without good. Yeah, that's good. We free 1. And then we make it E0. I think it will work. No, we do. So why we need to do that? Exactly. Now we're here. Now we're here. I guess. Okay, right? We're here, right? This is 3E8. 3E8. We're not here. 2E8. 2E8. Oh, we're here. We want to get here. Ah, I'm stupid. Okay, 0. 1. Let's see. No, it crashes, so one cannot be freed. What about 2? Yeah, 2 cannot be freed. We're wasting one of our reference. Dun, 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 dun. So what we can do is that we put our chunk here and then override it. So I need a 4 cannot be freed because 4 is misaligned. 3 cannot be freed because 3 is a bad pointer. Let's see what will happen with 3. 3 looks good. So we can have 3. Okay, there. And we need to another reference. What about with 3, 0? No, it's invalid. 1. Okay, 1. What will happen if we so right now the problem here is that we don't have enough reference. So 4 is taken by a misaligned chunk, so we cannot free it, and the 0 is taken by our chunk at free hook, so we cannot free it. So and we still need two references to perform a chunk overlapping attack. And I think we can make it work to free a 1 if we edit it. If we edit the size of 1. Yeah, we edit size of 1 to this thing 0 0 and 1 should be good. Size of 1 and now free 1. No, it crashes. Why? RCX info valid memory tries to access this thing, so we don't do it. We make it 4. What the heck? Okay. Not detected because it's already in. Oh no, we're having some trouble. This one's already there. So we 100 1 for 1. Cool. Now we have 2 references. Oh damn it. Do you know what happened just now? So the problem here is I wanted to show a new method, but I didn't think it over. So we encountered a problem that we don't have enough references to actually perform the chunk overlapping. So my idea was to we allocate something here. We allocate a node here, and we allocate another node that is going to override this part. We override the ref count to bin sh, and then we free this chunk, and then this chunk will be use bin sh as our payload. That's the original idea, but we need 2 references to perform the attack, which I didn't have. So that's why I'm freeing 1 to make it happen. All right, now we can perform the attack. Now we perform, we delete 1, we allocate 3, and then 1. This time I think it will work. No, it will, because there's no 1 at all. What? Delete 1, delete 3. Keep info 1, 2. Where is that thing? Where is our 1? Keep info. I think I'm being stupid. It can be.
Don't we still have a reference overlapping all of this that we can use to overwrite it?
Exactly. Yeah, we can use this one actually.
Yeah.
We actually can use this one. Which is 2E8 and 2B8, which is 2. Now? Not sure. Yeah. Two E8 and two E8, which is 2E8 here, and then 2C8 is 1 and 4. Okay, so what we're going to do is we use this chunk and then override here, and then free this chunk. Okay, let's do 2 paddings, n size payload. Edit 1 n size payload. Payload, which is not sh, but sh just 8 x minus 1 or plus 1, maybe plus 1. Plus 1, this thing. And then it's plus. So the idea is we, instead of calling system being sh, we're going to call system sh. But why there is ff here? We want to make the ref count a negative number so that it will be free. If it's not a negative number, the program will only reduce the ref count by 1, and then that's it. It will not be freed, and that's bad, right? This is oh no.
The ref count signed?
Yeah, the ref count is signed.
Huh, seems weird.
Seems weird.
Hey, why would you want a signed ref count? Don't you just free it as soon as it hits 0? Like, negative ref count doesn't even make sense, does it?
Yeah, you're right, but that's how it works.
It's just that, like, how they implemented it? Okay.
Yeah, that's how they implement it.
I mean, I think it lets you detect a bug, which they didn't do, rather than just wrapping around to a huge number that will never get freed. But yeah, that's the only thing I could think of, maybe.
Yeah.
Oh, we still need. No, so we still need to free that thing because the size associated with 1 is not large enough. What is it? 0, 1, 2. Maybe we can 2 use the same. We can't. Yes, we can. So we have to delete it, like what we're doing right now. We can't. No, we can't. Because we do that 40. We do 40. We do 40. Yeah, we can. Kind of stupid. Yeah. We unlock 1. 40, which is 0x3 30. And then we do edit again. No, we do this. Then edit. Now it works. Now the payload is at the location. You see, we'll allocate here, and we place our payload here. The ref count of this node becomes, I hope it's being sh. Th, which should be fine, because it will be reduced. RST, yeah, you'll be reduced to sh. Let's p free hook. Oh my god, it's not system. Why? Oh my god, I fucked up. I fucked up so hard. What happened?
Hey guys, I think I gotta dip out. Thanks, Kyle. This was pretty cool. This is a pretty cool challenge.
Good stuff.
Yep. Sorry, I fucked up. Should have like according to the plan. Do everything according to the plan. Let's see whether I can finish everything in 15 minutes.
Sounds good.
And shit, I gotta dip out myself as well. Thanks,
Yeah.
Kyle. You're awesome.
Yeah.
Cheers, guys.
See you, Kyle. See you guys.
See you guys. Sweet. Wait, 3, 4, 3. Omega. Yep, it's SH. All right, our payload allocation. And then we want to now we want to override free hook with SH again. Info. Now let's override this to 100 and then this thing. Why it's not freed? It's weird. This thing, because it's been A to C to CA to here. Over to EA. But why this part is not freed anymore, which is weird. Edit 3, delete 3, delete 3. Okay. Delete 3 and this part and then override that part. That sounds good. Sounds good. What I don't understand is that how this gets not freed anymore. Where does it go? This chunk. It should be. It's not in use and it's not in. It vanishes somehow. We don't have a reference to it. Oh, I'm stupid. I'm sorry, guys. I just need to edit it. God damn it. All right. P, free hook, system, and then do it again. 3. What? Yep. I'm sorry.
Wow.
Sorry. So the last part. So the fucked up part is that I didn't stick to my plan. My plan was to my original plan was to add a to basically perform a real chunk overlapping. But here, like overlap a chunk with a chunk that we have reference to. But this time I didn't do it. I do a chunk overlapping, and the inner chunk is a chunk that we don't have reference to. So we can hijack the free list, but we cannot free it like arbitrary. We cannot overwrite its content arbitrarily. So I had to do it in 2 steps. One step is to get a reference near the free list, which is
So why couldn't you override it arbitrarily? So I understand the first reason you couldn't, but don't we have this where is it, the edit 0 that does the free hook minus hex 10?
no, you can't, because we cannot we don't have a reference to the ref count.
But we
can't
have a
override the ref
reference
count
to
directly.
all of that data still, right?
What?
So on line 79, right, you do that edit, that is where you're basically, you have this overlapping chunk that's just overlapping like everything in the world, right?
Yes.
Why couldn't you use that reference to overwrite the contents, to overwrite the ref count?
Because it's freed. This part is freed. When we do a allocate 0,
Uh-huh.
when we do another allocate, the ref count of
And we don't
previous
have
count
another
will be-
reference? We can't use allocate on a different
Yeah.
number? We're out?
because it's we cannot get a. Isn't
Like,
this
how do you
exactly what I'm doing here?
later-
Is it
Mhm.
allocate 30 because it's being freed to 30, right? So I do a allocate 30.
I see, right, yep.
Yeah. So I had to do it in 2 steps. One step
Yep.
is to override free hook, and the other step is to override the content of another chunk, which
Yeah,
is
so when
exactly
you
what
do
I'm doing
that,
here.
that's that on line 86, when you do that alloc 1 hex 30, you're getting the same thing that you were doing on line 79 or
Yes.
line 78. Those are the same parts of memory. Okay.
Yes, but we
Yeah, that
cannot
makes
do
sense.
it like in one go.
Yeah, you have to do it after your allocations.
Exactly.
But yeah.
Exactly. Yep, that's pretty much about this challenge and how to exploit trunk overlapping.
And also, so the binsh trick, is it that free is setting the first 8 bytes of the chunk and putting that into RDI?
Yes.
Okay. So you can like basically always do